Hi, my name is Philip Maymin.
And I'm Stella Maymin.
I'm at Fairfield University,
And I'm at Greenwich Country Day School.
and we'll be talking about computational mindfulness. The idea is, can you become more mindful by doing certain things, such as,
Spot the difference images ranging in difficulty.
or looking at quantum randomness as opposed to regular pseudo-randomness. Good morning. We're here to talk about computational mindfulness. Now, I'm Philip Maymin. This is my daughter, Stella Maymin. You may have heard of mindfulness. Mindfulness is the new hotness. Have you heard the phrase mindfulness? You've heard what it's talking about? Now, this is not a neuroscience lecture, as you can tell by the apparent lack of fMRI machines, and it's not a meditation retreat, as you can tell by the complete lack of yoga mats. We'll talk about mindfulness and how we've thought about approaching it in terms of a computational way, but mainly through the perspective of Wolfram tools and technologies. That's the main focus here. Mindfulness, typically when you think about mindfulness, the usual definition is that it's something that you can get after 40 years of learning how to meditate. So you meditate for 40 years and you have 2 minutes of mindfulness. Good deal. An alternative approach, propounded by Ellen Langer, who's been referred to as the mother of mindfulness, is that mindfulness is very simple. It's just the process, the active process of noticing new things. If you look around the room now, if you notice 3 new things, boom, you're mindful, end of story. So instant mindfulness, like that. That's what we want to look at. The benefits of mindfulness, which we've learned over the past 40 years, have included virtually anything you can think of. Health, mental health, relationships, love, career earnings, you name it. Let's look at how, so when entering a new field, when looking at what research has been done before, it's useful to see just some numbers, like how much mindfulness has grown. So I'm always a little bit behind the times. I've been concatenating strings like a sucker for many years, but string template is much nicer. The easiest way to think of string template is it returns a function, and then you just call the parameters, 1, 2, whatever you want. So if we want to look at Google Scholar and see how many articles were published on mindfulness in a particular year, so 2019 to 2019, for example. The only problem, if we run import on it, Google seems to identify that we're not really a justifiable human being and doesn't let us do it. This is one of the nice new features in Mathematica. You can control a browser directly, programmatically, and have it do all your work for you. Now, the only problem is if I run this, it sometimes works and sometimes doesn't. The only reason it doesn't is Google becomes suspicious and starts asking us to prove that we're human, and I'm really bad at those. So let's just I'll tell you what the numbers were from before, and then when you're done, you just close the object, delete the object this way. So here's what can you see those numbers? This is what the articles counts for mindfulness has been like since 1960. It's rare to find an exponential chart as beautiful as this, right? So the last point is this year, 2019. It's a little down, but okay, it's not the full year. 2018, the point before, and 2017, the one marked in X. Maybe we have reached peak mindfulness, ladies and gentlemen. It's all downhill from here. But there's good news. So here's the good news.
So as Ellen Langer says, if mindfulness is the simple act of noticing new things, can we induce mindfulness with a spot the difference challenge? Does anyone see the difference between this image on the left and the edited image on the right? Yeah, the fish on the top is missing in the second image. So the heart of all this functionality is image contents, which so it finds the bounding boxes of contents in the image and guesses what it thinks it is. So although most of these are wrong, like this ice cream is a hot dog, this one's a cake, and these two are umbrellas, that doesn't really matter for my purposes because all I need are the bounding boxes to either edit them out or just take the content out completely. Here are some of the image edit functions that I've created for spot the difference challenges. Here's an example of the image map all function. You can see in these images there's one butterfly missing. The bottom one and the first one here is missing. And then the top one right here and the big one in the middle over here has been expunged. Got that together? So this is the website that I made in this past summer at the Wolfram High School summer camp. You choose the difficulty if you want all of the images in that difficulty range or just one randomly chosen one and an image. So here is an example.
Let's make it bigger. Let me turn on my EEG. Where'd it go? So you can see, we'll show you the demonstration live. You'll see my brainwaves. So those are my brainwaves. So I'll try to, I can't seem to calm down. But when I blink, you'll see it. Ready? Hang on. See the blinks? That's live. Okay. Walk us through the experiment.
Okay. So these are the easy one, but because there are so many contents, it's harder to find the differences. Does anyone see the difference between this image and the one on the right? Yep. And then right here is the image difference, so it shows us that we are correct. Does anyone see the difference between these two?
Where is it? Oh.
Nice job. We'll do one more. Does anyone see the difference between these two?
Subtle. Top where? Top middle? Is that right?
Yeah, that's pretty middle, yeah. So it's the plant right here.
Oh, nice. You see the white background? All right, so let's look at the brainwave. And we export it. We're using a brain bit, but we're going to try to export it later. Signal. Okay. Okay, go ahead. Okay, so this is an EEG. It measures brain waves, electrical activity, and uses these disks. Here's what was just measured on this line plot. Here's what I looked like. So we'll basically take the average of these four and across various trials, and that'll represent my brain activity. So these are the four sensors. EEG, so here's our first hypothesis, that when you're doing difficult spot the difference challenges, and her website has ranges from easy to impossible, and the impossible literally is impossible. It's like a microscopic changes that even computers can't detect. They can detect it, we can't. We presume, suppose you're looking at different spot the differences. Some of them are easy, right? There's just a big fish missing, fine. And some of them are much more subtle. We deem that when you're looking at the easy ones, you're kind of being mindless. But when you're looking at the difficult ones, then you're being mindful. You're noticing new things. Here's an example of what that would look like. Okay. A quick aside. There is a way to create web apps on using Wolfram. This is a pretty unknown thing, so let me show you how to do it. It uses something called JSONet or JSONL. Can you see this? Oops, wrong one. Can you see that? Great. So I'm mirroring my iPhone. So this is an app called JSONet. It works. It's a single app that you can just make a JSON file. That's your entire app, and it creates local web UI components both for Android and iOS. So here's the existing app that I have. This is a mindfulness app that I'm co-building with my partners Peter Lee and Chanwell Park and Ellen Langer. And this is all done, the source code is basically here. When you have JSON, you should think associations, so it's just associations. Now the amazing thing is, look, I'll make a new code. We'll add this welcome to Wolfram up top. It creates this QR code. And can you see my, here? We'll just scan the QR code for the new source. Hello, computer. How's that? Why is it too bright? Okay, it found it. And there you can see at the top it says welcome to Wolfram. We just changed the source code for an app live without going through the App Store, without going through anything. Now imagine if these components, they're fine what's built into JSONet or what's called JSONL now. You could do pretty cool things with it. That's no problem. But imagine if this could also communicate with the local Wolfram kernel in your iPhone. All the amazing things that you could do then. For example, this mandala, I didn't write the code for this. I got it from Stack Exchange. I think it was written by Anton Antonov. It's beautiful, but imagine how much more amazing it could be if we could also integrate with the Wolfram kernel, which it can do. This is all totally possible, and JSONet is entirely open source, so we could use it that way. Okay, great. Now, I'm about to tell you something that is the most ridiculous assertion, the craziest hypothesis you'll ever hear. I'm a little embarrassed to tell you. In fact, the only other people on Earth who know this hypothesis so far are my daughter, my wife, her mother, and our rabbi. So, but we're among friends. No, we're not even among friends. Wolfram is a family. We're among family. We feel like we're in a safe place. So I'll tell you our ridiculous hypothesis, and it's this. Where does mindfulness come from? Why does mindfulness work? Why does noticing new things cause all these amazing health benefits? It's a crazy assertion. Even crazier would be this assertion, that it all has to do with quantum mechanics. So when you measure an electron or a photon, and you know which branch you're on, right? Before you measure it, it's in a superposition. It's kind of everywhere. The same way if you're mindless, the world is kind of hazy. But when you see where it is, then you're on a particular branch. And you become mindful, you're on a particular branch. I know this is a ridiculous assertion because subatomic particles, which is the basis of quantum mechanics, has nothing to do with the macroscopic things that we're seeing when we're looking for new things. Ooh, nice dress, nice shoes, what a brilliant new car. That has nothing to do with subatomic particles, right? I get it, I know, it's ridiculous. But let's test it. So we're going to test it. So not just computational mindfulness, but quantum computational mindfulness. Here's our second hypothesis, that if you look at random numbers, you'll be mindless. But if you look at quantum random numbers, then you'll be mindful. Ridiculous, right? Totally ridiculous. But we'll try it. So to get pseudo-random numbers, we'll use Rule 30, standard cellular automaton. Here's how it looks like. So these random numbers here, each of these points is something between white and black. It's on a scale of 0 to 15. It's the same thing as you could use with random image, but we'll use this because we can then send in different quantum randomness. So far, so good? If you're looking at that, then unless you're doing something else, you're probably mindless. That's the claim. Now, if we do quantum random numbers, there's a website in Australia that you can ping, and it'll give you live quantum random numbers. And if you don't ping, then they just discard those numbers. They don't exist. So this one, I'll evaluate it live for you. So here we go. You are now about to be entangled with a bunch of, there we go. You're entangled with a bunch of electrons and photons from Australia. How does it feel? Hopefully a little bit mindful. Yes? Can you just define quantum random numbers? Yes. If you do a beam splitter, right, and an electron could go to the left or it could go to the right, this would be a 0, this would be a 1. So in a many worlds interpretation, both things happen, right? You're half of you, same you, but with half the weight, goes on one branch, half of you goes on the other branch. Does that make sense? As opposed to pseudo-random numbers, which are just computer algorithms, like the Rule 30 cellular automaton. The reason quantum the reason quantum random numbers might make more sense is if it's something underlying. There's no the quantum measurement problem is the biggest problem in quantum mechanics, right? Mads will tell you, right? Nobody knows why measuring something would collapse it. So there's different interpretations. The many worlds interpretation says there is no collapse. There's branches of you become duplicate copies. However you want to think about it, the fact is once you see something, the structure of that subatomic particle changes completely. It loses its superposition. It's no longer interesting. It just becomes, there it is, there's the electron. Schrodinger's cat is either dead or alive once you look at it. It doesn't continue to exist in a superposition. In other words, we become entangled with it, or you can say it decoheres with the environment. However you want to think about it, we're now there, right? In other words, we are here and not there. That's the same thing as being mindful. You notice differences. You notice new things that you didn't notice before. Okay, so what are the results?
Okay, so as you can see when I was looking at the easy pictures, that's the thin blue line here. It's very volatile. My volatility is 275, just bouncing around. When I was looking at the harder ones, I was closer, my EEGs were closer to an almost straight line, which we think of as the most mindful state. You can see from my dad too, although he's a bit more volatile in both, when looking at the hard images, he's much closer to that, again, that straight line. And when I was looking at the random images, when I was looking at Rule 30, my volatility was 483. And when I was looking at the quantum random images, it dropped 200. And when my dad was looking at them, at the rule 30, it's very volatile again, and it's almost a perfect straight line when he was looking at the quantum images. I think it's important to know that because I made these spot the difference images, I had seen most of them. And although there is no way I could have known all of the image differences and the edited images, I still had an idea of what the contents were, and my father did not. When I was looking at the random images, I did not know if it was a rule 30 or if it was a quantum, but my father did. So maybe we could say that not only looking at a quantum random image, but knowing you're looking at a quantum image will make you more mindful. And if you take away nothing else from this presentation, each of this took us maybe 2 minutes. So if you can take 2 minutes every day and just look at a spot the difference image or create your own quantum random image and just take 2 minutes to have all those benefits, the love, the relationships, just happier in general, can you imagine what that would do for our world? Thank you.
Thank you very much.